Yes, I can see is that there's a section about the Microsoft Azure.
So what we saw, one of the main ideas that was discussed in the last session was that there are few ideas we discussed in the last session. One was that data comes in three main formats: unstructured, semi-structured, and structured data. Right? And in this particular course, we are going to deal only with structured data. And that's what I was also informed by a grad that unstable. So I'm going to try changing my router. So I'll be back in a few seconds.
Thank you.
Let me check.
Actually, I write also to upgrade a state that to give this information little advance, then we could plan it, Yeah, I got only know about this Friday session very late. So, yeah.
I'm back. Okay. Today, what we will do today is continue on the journey of introduction to machine learning and artificial intelligence from where we left off in the last session. Okay. So what we saw, one of the main ideas that was discussed in the last session was that there are few ideas we discussed in the last session. One was that data comes in three main formats: unstructured, semi-structured, and structured data. Right? And in this particular course, we are going to deal only with structured data. Structured data is that type of data that can be presented in the form of a table, as a tabular, in the form of a spreadsheet. Right? That kind of a data is called structured data. In this particular course, we will deal only with structured data. That's what we started with. And what do we do with the structured data? What kind of machine learning, what types of machine learning will we do? There are quite a few. There are at least three types of learnings that are possible. One is called supervised learning. The other one is called unsupervised learning. The third one is called reinforcement learning. That's another one people call semi-supervised learning, and whatever. Okay. We are going to deal with the two most common, most important types of learning called supervised learning and unsupervised learning. Supervised learning is the type of learning that deals with building models that are used to predict a value for a continuous variable or the category of a data or a datum, category of a data. Okay, so we call it prediction tasks or classification tasks. These two fall under the broad category of supervised learning. In the unsupervised learning, we have generally a segregation of data into different clusters, identification of rules that are hidden in the data. These are the two common ideas that we will learn in the unsupervised learning domain. Therefore, what is supervised learning? Supervised learning is the learning when, okay, in fact, before this, I do not know whether we had, okay. We should know this particular format before we know what is supervised learning. So it should go earlier. Okay, let me do that right away. Slide sorter. Okay, structured data. So structured data, as I mentioned, is the type of data that can be expressed in the form of a table, right? Now, in the table, all the columns, that is vertical arrangements, are called columns. The horizontal arrangements are called rows. All the columns represent, each column represents one variable in the data. And each row represents one data point, one datum. Out of all the variables, one variable usually we identify as the target variable. If a target variable is present, then we are in the domain of supervised learning. When the target variable is not present, then we are in the domain of unsupervised learning. So this kind of a structure is called a data frame. In some contexts, we can call it a matrix, spreadsheet, or data set. These are all different names used for this entire spreadsheet, right? The variables, the columns, are also called attribute, features, dimensions, independent variable, all these different names. I am going to stick to the term independent variable. Why independent variable? Because they are independent. There is another type of variable which is going to depend on the values of these variables. So these are independent. The other variable, that is a target variable, that's also called the dependent variable. That's also called the outcome variable, tag, label. Okay. If it is a classification problem, then it's called a class variable. If it's a regression problem, then it's called a regressor. Okay. So different types of names. Now, so the variables, let me again do a little bit of change here. Let me move all this. Okay, it's not showing up. So the target variable, usually we write the mathematicians represent it in this such succinct form. We discussed about this, so let's not worry about this notation, but it essentially means the set of independent variables are a set of numbers, real numbers. How many of them? P of them. Okay? It's called the one datum is usually called a tuple. Okay, I'm sorry. This should also come as part of this. This is a part of this. So this is also called the tuple. That is all the independent values of the independent variables, or record, or datum, or row, or a vector, right? And when the number of variables is large, we use the term high dimensional data. So when we have this outcome variable, then we can do what is called supervised learning. So what happens in a supervised learning? What is learning in the first place? Learning is that there is something called an AI/ML model. We have not seen what a model is fully yet. I think we had a small introduction to it. So we have a model, and we want to train that model such that for a given input, we get a correct output, But we know correct only if we already know the value for the output. Therefore, during the training phase, what we do is we give to the model the attributes or the set of independent variable values and also the value for the dependent variable. The model, what happens, predicts the value for the dependent variable and compares it with the actual value. And depending upon how wrong the model prediction is, the system would adjust the model such that over many such input-output pairs, the model will start predicting as accurately as we want, okay, or it can. Okay. And then once we have reached the best performance possible, we could see whether the model is really reliable or not by looking at some data for which the labels are not given to the model. And that is called testing the model. Okay? And that kind of data is called test data. Okay? And this is the general procedure that we do. This is a generalized procedure we have for supervised learning. This can be a class variable like here in this example, or it could be a continuous variable. Maybe this is the prediction of a salary, or maybe it's a prediction of rainfall, maybe it's a prediction for the premium in an insurance situation, right? It could be any of these values. Okay? And on the other hand, unsupervised learning is the learning when we do not have the outcome variable. When the outcome variable is not present, then what we have is we have unsupervised learning. So what do we say? We tell the algorithm, we tell the model, using this idea, some idea, whatever that idea is, using this idea, segregate this data into 3 groups or segregate this data into 5 groups, something like that. We give such instructions and the model would go ahead and do that for us. Okay. And that kind of learning, it's not necessarily a learning here, okay, but we use the term learning anyway. So in that sense, this is called unsupervised learning because there is no supervision. There's no supervision to see whether the model is working right or wrong. In the previous case, during the training phase, we always were able to check. We were constantly checking whether the model performance was correct or wrong. So that was supervised. This is unsupervised. And we saw examples of data, what is meant by structured data. We saw examples of unstructured data also, right? And my memory is we discussed this. Please tell me whether we discussed this slide.
Yes, we did, but we were towards the end of the session, so you went through pretty fast.
Okay. So, again, I'm starting with unsupervised learning here. So, in the unsupervised learning, let's take a look at a simple task of what is called clustering. Right? What is clustering? Clustering is essentially segregate the data or find the rows that are similar. This is the actual algorithm we tell the model. We tell the computer system, okay, identify the rows that are similar to each other. The question then arises, what does it mean by being similar? Then we give a mathematical definition of similarity. Okay? And once we give the mathematical definition of similarity, using this definition for similarity, segregate the data. That's what we tell the system. And then using that idea, the system goes and the system segregates the data into different groups. And for example, maybe we would get clustering like this. This is a dummy example, so don't give too much credence to it. But what happens is, when we are able to do such clustering itself, separating them out itself might not be of too much value, right? It's probably of good value, but if we are able to identify some defining characteristics of each of the clusters, then we have some useful information to us, right? For example, in this example, all these purple dots would refer to people who have quite high income but low property value. Okay, maybe these people are good targets for selling property, right? And here are people who have a medium income and a medium values of property, right? They own properties of medium values. Likewise, here the orange points might refer to people who have high annual income and also possess high value properties, right? So then, if you are in property management or property, if you're a property salesperson, then you could look at this, and then you could see for each member in the data in the data set that you possess, which cluster they belong to, and based upon that, you could devise a sales strategy, right? In this particular data set, there is one point here where my mouse is present right now, or maybe I can annotate this. This particular point here, right? This particular point is kind of daisy. We have called it green, but it looks like it could be more orange than green. Sometimes when we do clustering, points like this might be left off. They might not be assigned to any cluster, and we would call them outliers. Yes, Prince Dubey, please go ahead, ask your question.
Yeah, so my question was about this dot, the green one.
Okay.
Because actually it looked like it is not actually following in either of the cluster, and it is sitting in between of that. Okay.
Yeah. Okay, so I answered anyway. I think I kind of telepathically read your mind.
Yeah, indeed. Thank you.
Anyway, so let me see what I can do. No, I'm not able to. So another type of one of the
Professor.
Yes, go ahead, please. Yeah, please ask your question. If you're is he speaking? Somebody said professor, but then I couldn't hear anything. Yes, Atif Mir, please go ahead.
Thank you. I just want to understand something basic here. You said that unsupervised learning is happening based on a mathematical definition. So am I getting confused, or unsupervised is not the right word, because there is some sort of learning going on, right? There's a mathematical definition, you've given it and said, based on that,
No.
create this cluster.
During the process of learning, we are not looking at whether the algorithm is giving the within quotes expected outcome. Okay, there is nothing to check back whether is something working right or not. We tell the algorithm, use this definition and do this task. It just goes and does the task.
Okay,
The
so the
will be
output,
complicated.
got it. So output is a cluster as opposed to some right
Yes.
outcome.
Correct.
Okay. Thank you.
We do not know beforehand whether this point here falls in the orange or green or purple cluster. Okay. Does it falls in the green cluster because of the definition that we used? If we had used a slightly different definition, maybe this green might have become orange. Right? So we do not know. So there is nothing right or wrong in the final outcome that we have. But in supervised learning, we do have that. Right or
yes.
wrong.
Yes, makes sense now. Thank you.
That's the difference. Yes. So one of the important applications of clustering is anomaly detection. That is, there might be some set of points which do not belong in any cluster, and those points, therefore, could be either they could be outliers or they could be anomalies. Okay, so the question is, do you want to call them outliers or anomalies? Depends upon the context. Okay, so I will leave it at that. Okay, so there could be some set of points which do not belong to any cluster, in which case these could be considered as anomalies. Okay? And anomaly detection could be is one of the very important technique that we use to identify frauds. Okay.
Rajan,
Yes.
is there any criterion which says that anomaly is a subset of outlier or outlier is a subset of anomaly?
As far as I know, there is no such definition. It could depend upon the problem at hand. Okay. What I would rather do, if there are set of points that do not belong to any cluster, then usually, hopefully, these are going to be a small subset of the entire data set. So when you have a few 100 million data points, you probably have a few hundreds or few thousands of such data points. And we could see, some ways these could be frauds. People can use different definitions to see whether these points are equally distant from every other cluster. Okay? Or you could study these points to figure out whether they are truly anomalous or whether they are outliers. Outliers could be because we are not able to just put them in any group. But anomalies could be because they are qualitatively different.
Rajan,
Yes.
usually the outlier is a univariate behavior, right?
In this case, there is no variate in the sense there is no outcome variable.
So usually when we try to give the IG gap, right, like IQ or gap, right, that's the time like we would say it is outlier. But when we try to say that like it doesn't belong to any cluster, it is more of a multivariate behavior because we try to create a cluster through a multivariate behavior. Is my understanding correct? Or
Correct. And IQR based definition of outliers, which you are going to see hopefully today, if you move fast enough, is one way of defining IQRs. Is one way of defining outliers.
Got
An
it.
outlier, in general, we can define it as something that does not agree with the majority.
Understood.
Whatever be the definition of that majority. For example, we might be building a model, and a particular point does not get modeled properly by this model.
Got it. Thanks, Raj.
Okay, sure.
Professor, just very quick question. When you define something as similar, is it up to the person who's kind of defining the requirement as to say what similarities you're looking for, or is it just left to the algorithm to kind of come up with?
Theoretically, that's what we would like to say. Before you start building your model, you can define your own similarity. But mathematicians have done this task for us many decades ago. So we will use the definitions that these people have given us. Okay, so we are going to define similarity in a very specific manner. We will deal with similarities when we talk about clustering, which will be about 7 or 8 sessions from now. But there are well-defined ways to define similarity.
Okay. So just in the table that you show in the previous slides, all the values are in the third row. Is there a reason why it's in the third row? It's random.
Awesome. You got a pattern. Nothing. I just randomly put some, no, I don't want to put like 10 rows and then give a sample data here. I just used here randomly. I didn't even realize until you mentioned now that it's in the third row. And
Okay.
this is just a copy of that. I just
Okay.
copied that table and removed that outcome variable. That's all.
Okay, got it.
Okay.
Thanks for
Yeah,
clarifying.
yeah,
Yeah.
yeah. That's a good catch. Okay, I didn't realize it. Yeah. So now, the other unsupervised learning technique is what is called recommender system. I think we discussed this also a little bit in the previous session. What it is essentially this is used in retail, and we can definitely use it in many other domains. But the idea is, we look at the column. The columns are variables. In this context, we call them item. So we see which variables are similar to each other. Okay, in retail, we might have different types of bread. They might all be similar to each other. No item similarity. Obviously, they are very different from razors, right? But razors, there might be few brands of razors which all might be similar to each other, right? So we could look at what are called item similarity. We could also look at what are called the similarity between the rows. And in the retail sector, the rows are representations of the purchasing pattern of a single user. So user one purchasing pattern is this, so on and so forth. So we could use user similarity, and we could use item similarity, and using these two ideas, we could now see which of the unfilled cells could be filled next. In a mathematical sense, that's what it is.
Sir, in this
So we are going
context,
to-
in
Yeah.
this context, what do the numbers represent in the box?
In this box, number represents user one bought product one 4 times.
Okay.
User 3 bought product 3 times, so on and so forth.
Got it. Thank
So this is what it is. In a single transaction, we'll have many a time what we would have is we would have this only as ones or zeros. Did the user buy this product or not? One, if the user did not buy the product, we will leave it empty instead of writing a 0. So only the filled columns or filled cells will tell us whether that user has purchased this product or not. And based upon user similarity, which user is similar to which other user is similar to user 2, we can look at that, and then maybe looking at all other users who are similar to user 2, because user 2 is now online trying to shop. Okay, then looking at all the items that are similar in this particular group of people who are similar to user 2, then we can recommend what products they could buy next. Okay? So this kind of technique could be used for recommender system. This is a very rudimentary idea, of course. Okay, we have much more sophisticated algorithms running in the background in many of the retail stores, but this is the grain of this is the seed from which this entire system of recommendations arise. Okay. Now, in terms of supervised learning, I think this is where we stopped in the last session. I talked about what is called a model. I was talking about what is called a model, and I mentioned that a model from last session onwards, we are going to use the word model to mean a mathematical idea. Okay, so idea, I'm not saying even an equation. I'm saying an idea. That's what a model is. Okay, in other contexts, when I talk to undergraduate students, I like to give this example. Now think of the word model. Immediately we think of advertisements and stuff like that. And let us say there is think of any of the celebrities acting as using a particular product. Okay, say somebody like Vishwanathan Anand, one of the greatest chess players in the world. Let's say he comes wearing a pair of spectacles made by SLR. Okay, so Vishwanathan Anand is a model. what does it tell you? That advertisement, that model tells you that if you look like Vishwanathan Anand, and if you wear this particular type of spectacles, or spectacles manufactured by this particular company, then you would look like this, or you would behave like this, or your vision might be like this. That's what essentially that is, right? So let us say this is for a vanity sunglasses, let us say, and this particular model looks looks outstanding, very attractive with this particular pair of sunglasses, then that gives an idea that this is how it looks like on a person like this. But let's say if it is somebody like what you call Jack Reacher, tall and hefty, 7 feet tall and 2 feet wide person, wears this particular set of frames, and I look at it, I go and purchase this. I'm 5 feet tall and 1 feet wide, very different. And when I wear this, I say it doesn't look good. It looked good on Richard, but it doesn't look good on me. Okay? And that's the exact idea of a model is. That's what models are. Okay? So in this sense also, why doesn't it work on me? Basically, that was applicable to Jack Reacher type of a frame, not for Rajan type of a frame, right? So if you want to actually find out what type of spectacles would look good on you, you should see how it fits on a model which is similar to yourself, right? Same idea here. So we start with an idea. Yeah, I want to predict the value for an outcome variable, and I start with the idea that the relationship between the outcome variable and the input variables is linear. As long as for whichever row, there are like 10 million rows, for whichever rows the relationship is linear, it will work well. For rows for which the relationship is non-linear, this will not work. Correct? And that's the exact idea. That's what a model is. So what we are going to do is we are going to start with saying that I am going to work under the idea that the outcome variable is a linear function of the input variables. What is a linear function? Linear function means every input variable is raised to the power of 1, exactly 1, right? That's linear model. Okay. If on the other hand, if I could come up with, maybe I saw that linearity is not applicable, therefore I say the outcome variable is a linear function of the first input variable and a reciprocal function of the second input variable. Maybe that's a model I want to work with. Okay, so this model means an idea. You express in terms of a mathematical equation like this. Then what happens? For each row, you check whether this relationship holds. And then on an average, okay, you have seen for all the 10,000 rows, and on an average, whether this idea holds true or not. You check that. Okay? And if it holds true, yes, your model is applicable. If not, of course, it doesn't work. Yes, Prince Dubey, please go ahead.
Sir, in looking at the first two equations, where a plus b x1 and c x2, right? So b and c, are these the weightage of the features? Is that correct?
Correct. They are the weights for the features. Okay. We are going to use the word weights, the same equation. We are going to use the term weights when we are using what are called neural networks. In the current context, we are just going to call them parameters.
Okay, perfect.
In the first equation, we have 3 parameters, A, B, and C. There are 3 parameters. Finding the values of the parameter is called fitting the model or model training. Model training means we are going to identify the values of A, B, and C such that we get agreeable behavior, the best possible outcomes. What do you mean by best possible outcomes? That is, using some values here, we would make predictions for Y. And we will see how much error we have made. No, there's already the Y, measured values of Y are available. We will compare these two and see how different they are. If they are close by, then okay, our model works well. I'm saying on an average, in the average sense. In the average sense, if the values are close by, that is the predicted value for Y and the measured values for Y. If they are close by, then on an average, then the model is agreeable. We can use that. If they are not close by, then of course we cannot use that. Again, now if you take a step back and if you're a stickler for details, you will ask the question, what do you mean by close by? Okay. And that's where the mathematics comes in, some definitions. That's where the actual supervised learning comes in. So we need to define what is this process. What do you mean by the values, predicted values close to the outcome measured value? So what do you mean by that? Then what we will say, we will define something called the error. And if we can talk in terms of error, then we want to see on an average, the error should be minimum. Okay. So then it boils down to the question of saying what values of A, B, and C, that is what values of parameters make the errors minimum. Okay. Finding those values for the parameters is called training. It's called learning. If it's supervised learning domain, it's called learning, right? So that's what generally learning is. So you have a mathematical model. The mathematical model is expressed in terms of the variables and the parameters, finding the values of the parameters such that the error on the average is minimum. That process is called model training. Once we have found the parameter values, then we have what is called a trained model. Then what we can write, instead of writing symbols like A, B, C, we can actually write the actual values. We can write Y is equal to 3.7 minus 0.35 x1 plus 42.96 x2. Okay, something like that. That is the model fixed. That's the best model. Now you can, when a new data comes in, we can substitute the values of x1 and x2 and we can predict the value of Y. Okay, that's what supervised learning is all about. And this is the idea of a model. So I want you to get, many a time people would say regression model. Okay, people would say that classification model. And they implicitly mean this, but they might be talking about the actual final outcome. Y is equal to 3.7 plus minus 0.35 x1 plus 42.9 x2. That kind of is what they might actually be talking and using the word model. That is the learned or finalized model. Okay. So
now, Rajan, in the previous one, we expect the F, which defines the relation between the x1, x2, x3 to Y to remain stationary. Only then this training would work. Is that correct?
What do you mean by stationary?
It doesn't vary over the samples what we have collected. Now, for example, I have a dynamic system where the F steers based on some external factor. For example, like I have a kind of a room temperature controller, and it has a F function, but it linear till certain point, and beyond that it either saturates or it shoots up exponentially. In that,
you have still not used a particular. Yeah, awesome. Okay, but you have not used a very important keyword here. Please go ahead. So far,
in such cases, we might be thinking that the B has an error, but it may not be an error of B. The function f itself has gone into a different region.
okay. What Muhammad Niaz is talking about, I think he's bringing in two different ideas, and both are very valid. He mentioned about something called stationary. Stationary is something that does not change with time. Okay, so it remains constant. Okay, I measure the as you was talking about. No, that's a sensor. Let's say it's measuring the temperature at a point, and the sensor's outcome, the values the sensor measures, could be dependent upon multiple things. Okay, but the sensor, okay, it's stationary. That means the value it measures remains kind of constant, provided the other things are constant. Okay, it's a slightly technical term. We will talk about the stationarity in the session when we come to what is called time series data. But he is also bringing in another very important aspect right here, and I will say this so that I don't have to discuss this later. Okay, this is called the idea of domain. What is meant by domain? Domain is the range of values over which x1, x2, x3, etc. varies. Okay, let us say we are trying to model the mass, which we erroneously call weight of a person. Okay, and x1 could be the height of a person measured in, let us say, centimeters. X2 could be age of the person measured in years. X3 could be the gender of the person, which is a categorical variable. It could be 0, 1, 2, etc. 0 means, let's say, male, 1 means female, 2 means something else, whatever. Right? It could be categorical variable. Now, let's say just that. Now, x1 being the height of a person, it could range from 30 centimeters or 25 centimeters for infants to about 185 centimeters for a very tall person, right? It's valid up to that. Okay. So let us say in our data, we are looking at a set of people working in an office, okay, and their values for x1 heights range from, let us say, 140 centimeters to 165 centimeters, let us say, or 175, 80 centimeters, something like that. Okay. So that's a short range, 140 to 180 centimeters. And age ranges from, let us say, 22 years to about 62 years, let us say. Okay. Gender 0 or 1, keep it that way. Now what happens is, we have used this data to predict the mass or weight of the person in kilograms. Okay, so we have this 100 people's data, and measuring their weights or masses, heights, and age, and their gender, we have built the model, let us say. Now somebody brings their child to the office. Okay, this child is 8-year-old, and the child's height is 80 centimeters, let us say. Okay, I don't know whether it's too short or too small, no, or 100 centimeters, whatever it is. Now, can I use this model to predict the weight of that child? If you ask the question, that's where Muhammad Niaz was talking about. Okay, no, you cannot use this model for that particular child. Why? Because that child now lies outside the domain of values for which the model was built. The model was built for people ranging in heights from 140 to 180 centimeters, age from 22 to 62 years. But here there is a person who is 100 centimeters tall and whose age is 8 years. So this data point is not in the domain for which the model was built. Therefore, it's outside the domain. We cannot use this. Can you really not use it? Of course, you can use it. You could go ahead and use it, but don't expect it to give you accurate results. Okay, that's what I was talking about. Because inside the domain, whatever model was valid, maybe was valid, but outside the domain, the relationship could naturally be different. If that is the case, whatever model was valid for the domain may not be applicable here, but we can go ahead and apply and see what happens. If the errors are high, you know that, okay, this is possible, so I'm not going to be too much worried about it. If the errors are low, then you could go ahead and jump in joy and say, hey, yes, my model worked even for this data point. I'm lucky. Like Google used to ask in its search engine, right? I'm feeling lucky today. That kind of thing, you can say that. If it works for you outside the domain, you are extremely lucky. If it doesn't work,
got it, Raj. Got it. Thanks for this. And I have one follow-up question. I'm not sure, like whether it, it is too early at this point. Series of lectures.
Ask it.
Yeah. So, for example, like I have a James Webb Space Telescope, and I have tuned a lot of models to detect the galaxies, life forms, and everything. And all my models are based upon whatever I know from the invented physics or the observed systems of solar or equal other stellar systems.
Yeah.
And now I look at somewhere on the other side of my galaxy and try to use that model and find it out. And how will I be knowing that my model? Because most of the cases we try to use AI to infer something which is not seen by us, right? In that case, like even somebody says that this is how a black hole looked like, right? A image stitched by various models. So in that case, how can we be sure that, yeah, the model has functioned correct?
You are going again this out of domain kind of a question. What happens is this, especially in cosmology and in these hard sciences, you have a very strong theoretical foundations on which you can lean. Therefore, anytime, in fact, what we are looking at in these cases are in many a time in cosmology, for example, we are excited to find anomalies, because those anomalies can now be not only tested against these dumb artificial intelligence models, okay, but you can now use them to actually fight against the established theory, pitch it against the theory, and see whether the theory has to be tweaked to explain this particular observation that you have found. Okay, so that's again a very, very different kind of a question, and this all the time happens as far as I understand in cosmology. You want to find anomalies, and you find the same things everywhere. It's boring there, because the idea there is especially in these cases, the idea is not just to find evidence, more and more evidence for established theories, but to see the limits of these theories.
Got it.
Yeah. Okay. So what do I mean by different models? We discussed this also in the last session, if my memory is correct. Okay. And so we would try out all these different kinds of models. Each one is a different model. That is, there are different ideas, because the first model says that I use 5 variables linearly. The second model says I use 4 variables linearly. The 26 model says I'm using the first variable and the 5th variable linearly. So these are all different models. Okay. And then what we can do is, for each model, we can see how the error is. And then out of all these models, see which of these has the lowest error in our training, during the training phase. And then you can use that as your best fitting model. Okay. So that's the idea. I have talked about it in enough detail. So prediction of a value of a number continuous number. For example, here is the prediction of sales in millions of dollars, fictitious data. No, it's not a fictitious. Yeah, it's a fictitious data. Yes, based upon the ad expenditure in the different campaigns. The ad expenditures are in hundreds of thousands of dollars. Okay, and now we have this data. Without this blue line, it would look like random. Okay, but then you could fit this model. Given the ad expenditure, I expect to make this much of sales. That's the kind of information that this blue line gives you. Okay, and what I have said, please catch my words. Please pay attention to the words I'm saying. Given this much of ad expenditure, this is the amount of sales I expect to make. Okay. Yes, please go ahead, Jansi Ram or Jansi Rani. I did not catch the name properly. I'm sorry.
It's okay. Jansi is fine.
Jansi.
So first of all, thank you. This is exactly, I'm looking for this real world use cases. So maybe you said like the model we pick and it is giving the expenditure or maybe the predictions. Can you please, if you do not mind, earlier screen you have written this 26 models, okay, and also you said about linear and non-linear many. So any one of the model you can take and you can explain this, how it is really works, just 1 or 2 lines, because I know the real world example is my homework, but still I am struggling to understand without the real world, without
We
this.
will come to that. That's we are going to spend a lot of time on this particular type of exercise. Okay, today on the next session, we will do the foundations, that is the alphabets, as I mentioned, namely statistics and probability. And immediately after that, we are going to jump into studying models of these types. And we'll spend 2 or 3 sessions on this. Is it okay?
Yeah, it's okay, but still also it'd be nice if you can give at least 1 or 2 sentences, because even I'm trying to catch last 2 sessions. It's somewhat, I'm not a good mathematics student, okay, so that's why I could not able to catch. Yeah, anyway, I can wait.
Yeah,
but it's fine. Thank you. Yeah.
Let things sink slowly. Don't worry about it. Yes, please go ahead.
Okay, so for Gen Z, I'd like to explain a little bit. Just give me about 60 seconds here. Now, we are talking about machine learning, okay? An example of machine learning could be identifying whether it is an apple or an orange, okay? Apple or an orange. So let's say model number 1, you're looking on the screen right now.
Yeah.
What makes the item look like an apple, okay? X1, it could be red in color. X2 could be the size and the shape. X3 could be the gloss of the picture. Okay, X4, maybe if you have leaves or no leaves. So these are the parameters that will tell your machine that this is an apple. Okay, model 2Y, you have X2, X3, X4. It could be data that will tell you that this is going to be an orange. And orange has orange color. It has a little on the surface. You have pock marks over there. Okay, so what you are trying to do is that you're showing the machine different apples, many apples, and many orange. At the end of the day, you would want to know if this machine can be taught and can it learn to tell the difference between an apple or an orange. You get me? So that's why we're having so many models here, is to say that can model number 1, after 1,000 training, showing 1,000 apples, will give you can the machine identify that this is an apple? So if you come from this angle of how the machine will learn by looking at different pictures and different shapes of apples, at the end of the day, coming to making a decision that this is an apple. That's why they're quite predictive. I can predict, looking at this image, this is an apple.
Okay.
You get it? This is a very simple explanation of if you go along this lecture of trying to understand
Jansi.
this machine learning, yeah, then you'll come to understand all these are mathematical.
Jansi, does it help?
Yeah, because I was thinking this X1, X2 is like, in the mathematical context. So
Absolutely.
No.
That quantities.
Yeah,
think,
so
yeah.
it is explained in mathematical form.
I think,
Identifying.
Sam, I should let you lecture. You have done a much better
Yeah.
job than I could do.
Thank you. Yeah, because
I
these
was
are my
like,
classmates. I know that they come from different practice, healthcare, industrial manufacturing, aviation. So this is just like machine language. I just want to explain in such a way that what we are trying to do here is predict the picture that you're going to present to the machine, and all these are expressed in mathematical models like that. So that's it. Basically, that's how it's explained. So if the machine look at it, there is, you see, x1, x2, x3, x4, x5 with the different weights of b1, beta 1, beta 2, beta 3, then a y will come out and say, oh, this is an apple. Then you look at model 2, model 2 can tell you that, oh, this is a orange. Yeah.
Great. Thank you, Sam. Thank you, Rajana, for this
Thank
short.
you.
I was
Okay.
a little bit, I really want this basic. That's what I interpreted. Sorry for that, but now I'm
No
little
issues, no
clear.
issues.
Thank you.
No issues.
Better. Thank you.
So we are going to see a lot of such examples, and I'm going to take one very classic example quickly and talk about that soon. We'll come to that in a minute. Okay. So mathematically, again, it might scare people. This is how we write y is equal to f of x plus epsilon. F of x is the model that we talked about in the previous slides. Any of these kind of equations plus epsilon. What is this epsilon? Epsilon is the error. The model predicted value is given by this blue line, but very rarely do the red points coincide on the line. Right? There is one point here that coincides. There are a few here that coincide, but all the other points, they do not coincide on that blue line. Right? So that difference is the error, and that error is the model prediction plus some error is the actual measurement. Okay, that's what the true model is. And what is the error? Error is usually given in this form. Okay, in the math, it's again, it might be scary to people who are not familiar with math, but we'll talk about this soon. This is called a normally distributed value. This is a number. Epsilon is a number that comes from a normal distribution which has a mean value of 0 and a standard deviation of sigma squared. So I'm introducing new terms here. Okay, error, that's maybe easily understandable, but normal distribution. What is a normal distribution? You might have heard the term. Some of you might be familiar with the term bell curve. That's what it is. Normal distribution is the term. You can think that's a jargon for the bell curve. It has a very specific shape, and it has a mean value. All the errors, if you take all the errors, it will have a mean value. Take the average of them, it will be 0. And you take the standard deviation, that will be some number. That number we call it sigma. Standard deviation square is called the variance. So it has a variance sigma squared. Okay? That's how we write this. This is how we write mathematically. Okay? If you have more than one variable, if you have two variables, if it's a linear equation, then it's not a straight line, because there is one independent variable, another independent variable, there's a dependent variable here. So we are now in a three-dimensional space. In a three-dimensional space, linear relationship is nothing but a plane. Right? That's what it is. If we have more than two independent variables, then we'll have to have fourth variable, four-dimensional space. If you can imagine, Muhammad Niaz was talking about cosmology, right? Not cosmology, astrophysics we can call it, because these are observations of stars and galaxies. Okay? So if you can imagine in multi-dimensional space, if you can imagine a plane there, that's what it would be. We call that hyperplane, because it's in a multi-dimensional space. Okay? So linear relationships mean plane surface. Non-linear relationship would be curves like this. Okay. In a multi-dimensional space, you can think of it like any kind of a curve. Okay? That's what a non-linear relationship would be like. Okay, I'm going to skip this section here. Okay, this is for prediction. This is for classification. Here is an example of what is called a binary classification. We will talk in detail about it when we get there. There is another chat message. Let's take a quick look at that. For some reason, my one problem is solved, but this other problem is still there. Doesn't show up. Okay, anyway. So again, we have a model. What is a model? Y is whatever this on the vertical axis is modeled as f of x. Now that f of x is a non-linear function, that is this red line or this maroon line. Okay, that's what the f of x is. This is an extremely non-linear function. This is not a straight line. Plus some error. Now here is the value. Here is the measured value. Here is the predicted value. Right? Here is the measured value. Here is the predicted value. Therefore, there is some error. How about the error? What about the errors in this case? They also come from a normal distribution of mean 0 and some standard deviation. Okay? That's what it is. So when you have classification problems, how do we classify? If there are binary classification, how do we classify? You just draw a boundary between the two classes. No, here is a
Sir,
very
just
here.
so
Go
this
ahead.
question, sir. Sir, what you showed earlier was a line of the best fit. Was it that, sir, in the previous slide where you showed
This one?
yeah, the previous one? Yes, sir, to the right. That's a line of best fit, right?
This is the best fit. This is the best fit line.
That's
This is the
okay.
best fit plane.
Okay.
This is the best fit plane. This is the best fit line.
So the trained model will give us that equation that will help create that line and be able to predict. Okay.
Exactly. Your understanding is perfect.
Okay, sir. Thank you.
Okay. So in our in binary classification, okay, so why sigma squared are used in normalization function? It's not a normalization function, it's a normal function. Normal. Sigma squared means variance. Sigma is standard deviation. The mathematicians like to use variance rather than standard deviation. Why? Variance is always a positive quantity. Standard deviation, when you take the square root of something, it could be positive or negative, right? When you take square root, now 4 is a number. If you take the square root of 4, it could be plus 2 or it could be minus 2. So to avoid that, they always stick to the squared term, therefore variance. And yeah, it shows that kind. Yeah. Now, in terms of classification, again, even though the model that we build is something like this, the boundary between these two classes is a straight line. In this case, it's a straight line like this here. Okay, in a two-dimensional data. Okay, it is a straight line here again. Okay, so this is one category. This is the other category. You can think of it as a number of this is the data of different components in an assembly setting, no, in a manufacturing setting. So you could look at the number of complaints a particular component has received versus the age of that component. Okay, so the classification is done by this boundary. Anything below this is not fail. Anything above that is fail, right? So we can do it this way. And there are multiple techniques for classification. Okay, so we have something called logistic regression, which is a linear classifier. There is one straight line or one plane that separates the two categories. Okay, But we can have multiple other techniques, non-linear classifiers. We'll talk about them as we move along, something called decision trees. Okay. And there are a few other, these are the two common classifying schemes. There's another one called K nearest neighbors. I usually don't want to even talk about that because in real world it's a very computationally expensive technique. Unless your data is very small, K nearest neighbors is of not great use. But anyway, so these are all what we call as classical machine learning techniques. Okay, but in the last 7 or 8 years, or actually in the last post-pandemic era, people have moved away from classical machine learning techniques, and people have moved into what is called the deep learning methods. Okay. What are deep learning methods? Deep learning methods are machine learning methods that use models of neurons as the foundational idea. Okay. The greatest learning system that we know in the world is the human brain, or any brain. Okay. The human brain is the most familiar one to us, the most powerful, the most adaptable, highly plastic, and a great learning machine. And what is the unit of the human brain? It's a neuron, that is a nerve cell. Okay. And if we can build models of a nerve cell and try to simulate how the human brain works, can we create artificial learning tools? Can we create learning tools artificially? And the answer is true. Yes, we can do that. Okay. So this is kind of a very, I don't like these pictures for some technical reasons, but but it gives a very general idea about what a new nerve cell or a neuron looks like. Okay, you show that how your data is distributed. If your data is not distributed, okay, I'm going to stop here. So, what is it? What does a neuron have? A neuron has. What does a neuron have? A neuron has a body. Okay, that's usually called the nucleus. That's where all the molecules, that are present. You might remember mitochondria, for example, which all of us have studied as the energy house of the cell, right? Then some of you might remember Golgi apparatus and names like endoplasmic reticulum, all these different things, if you remember. They have their own specialized stats. Some of these are cleaning agents, some of them are nourishing agents. Mitochondria is the energy center. Basically, it breaks down the incoming glucose molecules or protein molecules and convert them into different ATP. That's what it is, adenosine triphosphate, so that energy can be utilized for functioning. That's not important for us. Something happens here. Something happens biologically. We are not interested in the biology. We are interested in the mathematics or function of it. The nerve cell has a lot of inputs. It gets a lot of inputs through what are called dendrites. Dendrite basically means a branch. That's what it is. So through a lot of branches, it gets a lot of inputs. Okay? And there is one dendrite which is very unique, which is distinct from all other branches, basically because it's thin and long compared to the others. And that is the branch through which the output of the neuron is given. Okay? The output goes through this axon. This is called the axon. And that axon again branches into different dendrites. These are called telodendrites, far-off dendrites, far-off branches. And each one of them might connect to different neurons. In this case, unfortunately, it is shown that all of these are connected to the same neuron. But in reality, the usefulness is when these different telodendrites connect to different neurons. Okay? And again, this neuron will be like the same thing, so on and so forth. So we can build a network of neurons. That's what neural network is. Okay, technically, the connections are called synaptic terminals. and let's not worry about it. In your next course on deep learning, depending upon the faculty you get and your interest, you can learn the biology of it a little bit deeper. It's a fascinating idea. The human brain contains about 100 billion neurons. That is 100 into 10 power 9, right? So 100 into 10 power 9 neurons, 1 followed by 11 zeros, that many neurons, and about 1,000 trillion synapses. Synapse means connection. So 1,000 trillion synapses. 1,000 trillion is 10 power 12. So 1,000 trillion is 10 power 15. Okay, so 10 power 11 neurons and 10 power 15 connections. So on an average, one neuron makes 10,000 connections. Okay? You can think about the complexity of the network in the human brain. Okay? 10 billion neurons, and each one making about 10,000 connections. Okay? That's humongous. That's humongous. And what we do is we create the mathematical model of the neuron. Okay, here is the cell body, and here is the body. Okay, and here are the inputs coming in, dendrites, and here are the inputs to the neuron. Okay, and then the output, the axon of the neuron, we get an output. Okay? So this is the similar structure. So the inputs come in. Okay, in our model, each input is multiplied by a coefficient. We call these coefficients as weights when we are talking about neurons. In general, we call them parameters. Okay? Here we call them weights. The coefficients of these inputs, we call them weights. Okay? These weights are, these inputs are multiplied by the weights and they are added together. Okay? And then something else. And then another constant is also added. That is called the bias of the neuron. And then this is sent through some kind of a function. Maybe it just passed through as it is, or maybe it is passed through some kind of another function. That's called activation function. Okay, and then the activation function is sent out after passing through a threshold. What does it mean? If you have studied neurobiology in your higher secondary or in your college days, you would probably know this. But this is what happens in a neural structure. Okay, a neuron, whether there is input or not, it is always sending out some output. But these outputs are random. Okay, these outputs are random. And the magnitude of the output ranges within a small range. Okay, it's within a small range. And that constant output that's there in spite of not having any input, that's called the bias of the neuron. Okay, in the biology, we call it the neural noise. It's called neural noise, but here we call it the bias. Now, in biology, what happens is when the input comes in, the neuron does something. What it does, we do not know. We have the model. The model is this. Each input is multiplied by a weighting function, by a constant. All the inputs are then added, and it's added to the bias. Okay, and then that is transformed by a nonlinear transformation. In the biological side, it's usually usually a nonlinear transformation of this sum of the weighted inputs. Sum of the weighted inputs. That's nonlinearly transformed. That's called the activation function. Now, only if the activation function is beyond a certain value, the neuron will give an output. Otherwise, the output will still be like a background activity. And that value, beyond some value, what is that? That's called the threshold. This is how a biological neuron works. And we can do the same thing in a model like this. Okay, you will learn in depth about these models as as you move into the next course on which will be on deep learning. Yes, Prince Dubey, please go ahead.
Sir, you said non-linear transformation will come into picture once we have the weightage are assigned to the different features. I want to understand that part with an example. Can you give small example with that?
Okay, I don't want I want to say that I don't want to give the example, but anyway, I will give the example. Let's go back in this. Okay, if you see this, okay, this mathematically, pardon me for, I'm going to make you feel, why did I ask this question? Okay, so this is going to be something like this. Let me say, one word, one more word, 1 plus, is it 1 over 1 plus? Yeah, I think so. Let me, I don't remember. Let me say, e power Okay, give me just a minute. Let me check this. Not relations, attributes, not this, formats, not this, others. Dots axis. Okay, yeah, got it. Okay, let's see whether this is okay. So if you look in here, okay, the inputs. This is the actual f of x here. Okay, the maroon line is given by this 1 over 1 plus e power something. Okay. Okay, this something here, right? This is what this maroon line is all about. Now, if you see W1 x1 plus W2 x2, that's a linear combination of the input, weighted inputs. W1 is a coefficient for x1, W2 is a coefficient for x2. This could be the color of the image. This could be the shape of the image, like what Sam was talking about. Okay, so we want to say whether it's apple or oranges. Okay, so it could be the x1 could be the color, x2 could be the shape, x3 could be the size, x4 could be the presence or absence of leaves, so on and so forth, right? As the example he gave. For each one, we have the coefficient. This is the linear function, weighted sum of the inputs, like what we have here. Okay, weighted sum of the inputs. That is then passed on through a non-linear function. What is a non-linear function? This thing, 1 over 1 plus e power something. Okay, that's a non-linear function.
Okay, so I got it. So it means talk about the deep actually around the image classification or something which is very much unstructured. We would need a help of linear plus as non-linear function combined together to find out certain output on top of it. Is that correct understanding?
Well, we don't have to say linear plus non-linear. It is a non-linear function. Okay, but how it does is, first it does some linearity, and then over that it does nonlinearity.
Yes.
Okay, so it's a sequential process. It's not
Okay.
an addition, but it's operation upon an operation.
Okay, so it means this example that Sam has given, if I feed my model orange and apples picture, then it will go into neural network and then it will classify based on that. But in case
Correct.
if I give the features explicitly instead of any deep learning model, if I give the features, for example, if I give the color as orange, if I give the weight of the fruit, so it means I'm specifically, explicitly defining the features straight away and then feeding. So it will be like a non-supervised learning, right?
No, it is supervised learning only.
Okay, supervised. So
Supervised learning.
so it
Supervised
means
learning only.
yes. So in case in the first example, because I'm not giving anything, I'm just giving a image. So it's it is going to classify the image based on this function and then generates the results. And in
No,
other
no. See, the problem is this. Let's take a step back. Do we know the values of W1, W2, W3, etc.? We do not know to begin with.
yes, exactly. In case of image, we don't know.
So we need to figure that out. To figure that out, we need to tell the neural network, your output is correct, your output is incorrect. We have to tell the neural network. So this can only be a supervised learning. If we are doing classification, it can only be a supervised learning.
Got it, sir. I think my confusion has gone. That's really I wanted to understand.
Yes.
To define that what exactly the difference between these two. Thanks a lot for that. Thank you.
Okay, sure.
Sir,
Another person had raised a question. Yeah, please go ahead.
Sir, nowhere in this equation you're talking about an output here. You're still remaining with the input, right?
Yes. Here is the input. Okay, and here is the output. Okay, the activation function is some depending upon if the activation function is like this. Okay, and we have set a threshold which is like this. Okay, then the output would be either an apple or an orange. Okay, the threshold, the activation function, and the activation is the output here. So this will be either an apple or an orange if you have given the threshold also. Okay, so it is there, the output is there. But the question is, where is that? Then somehow we have to go back and tell the neural network your prediction is correct or incorrect. Okay, that's a completely different ball game. That's you might have heard, some of you might have heard a term called back propagation, which you will study in the next course. It's 7.5 weeks away from now, or at least 7.5 weeks away from now. You will study that. So how do we fix these values of W1, W2, etc.? That's called training the neuron or training the neural network. Okay, that you will learn in the next course. Okay. So if I can model a single neuron like this, then I can have multiple neurons. Okay, and then I can build complex. I don't like to use the word complex because in mathematics complex has a specific meaning. So let me use complicated. If we can build a complicated network to do a very complicated task like this, I want to separate out these two classes. This is not so clean like the previous examples we saw. The earlier example we saw was very clean, like not fail on one side, fail on the other side. But in reality, most often we are going to look at data which is like this, right? And classical machine learning techniques cannot deal with such data, but a neural network can. That's the power of neural networks. How they do it, I'm not going to talk, but they can add. They can do these kinds of tasks and much more complex tasks they can do. Okay, so I will just leave it at that. Will not go into details of this, but just remember these terms. Just get familiar with these terms. The x1, x2, right? In this diagram, I gave you this x1, x2. This layer is called the input layer. Okay? Obviously, this layer is called the output layer, and then anything in between is called the hidden layer. These are the actual neurons that do the computations. Okay? These are the actual neurons that do the computations. If the hidden layer has more than 2 layers of neurons, then we have what is called a deep neural network. Okay, so the hidden layer has more than 2 layers of neurons. If that is the case, then we have what is called a deep neural network. If it has 2 or 1 layer of neurons, then it is called a shallow network. Shallow network, deep network. Okay, and with this deep neural networks, we can do multiple things. Now we can provide. Now this is very complicated. Now the complexity in this problem could be humongous. Immediately you could ask questions like, how many layers should I generally have? My answer will be, I don't know. Okay, that's fine. How many neurons should there be in each layer? My answer is, I don't know. Okay. Then you could ask, if you look at this, every neuron is connected to every neuron in the next layer and also in the previous layer. Okay, should this always be the case? My answer is, I don't know. Okay, so anything you can ask, I'm going to say I don't know. Why? Because we could use some algorithms to fix these numbers. How many layers should be there? How many neurons should be there in each layer? What kind of connection should we have? Connections seem to be flowing only forward. Can they flow backward? Maybe they can. Okay, so all these different things define different types of neurons. Okay, so this is called a fully connected, because everything is connected to everything else in the next layer. Feed forward. The information is fed forward. It's moving only forward. Feed forward neural network. Okay, fully connected feed forward neural network. We could have sparsely connected feed forward, or we could have fully connected neural network with feedback. Now we can have multiple types of things we can have. How many layers? That's something we have to play with. How many neurons? That's something we have to play with. Okay. Yes, was it Prince Dubey who raised the question? Please ask your question.
Yes, sir. Basically, we cannot identify that how many hidden layers we got in neurons, hidden layers. So basically, in that case, if I want to understand that how my model reached to a particular output, what calculation it does, so is that explainability is missing here?
Explainability is missing the moment you go to neural networks. It's gone. It's gone for a toss. There is no explainability in neural networks.
Okay, so in case if I take a business decision and I need to show that to my senior management, and if they ask me that, what are the calculation, what are the formulas you took to come to that solution, it's not possible into neural network. Is that correct?
No, it's not possible. You are correct.
Okay.
Okay, and then we have some specialized neural networks. Okay, neural networks that can do special type of tasks. One of the most common special type of tasks is what is called convolutional neural network. Each neuron has a very special property, and these types of neural networks are used extensively in image analytics. And of course, if you have imagination, we can use it for any kind of other analytics as well. Okay, but image analytics is predominantly dealt with what is called convolutional neural networks. Okay, and I'm going to quickly wrap it here. With the layers and layers of neurons being added, we could build what are called auto encoders and auto decoders, or encoders decoders pairs. And what does it do? So we have the raw input, and somewhere, now let's think about this particular neural network. Let us say I break it somewhere here. Okay, since it's a fully connected network, the output, when I break the network somewhere here, the output of these neurons are in some way a representation of the input. Okay, it's a representation of the input. If the number of neurons in this output, when I have broken the network, if this is smaller than the number of inputs, then I have achieved one thing called dimensionality reduction, data compression I have done. Okay, now what people, that's what people initially started working with, and we call this encoding. But then what people did was, okay, if this is the case, let me take this encoding and give this as the input to some other neural network which has the same number of inputs as the number of encoders here. Okay, some other neural network which has only 3 inputs and it does some other task. If I give this as input, what will it do? Okay, when they started asking these questions, remarkable things started happening. What started happening? We could have transformers. For example, I could have an encoding for English text, and the second part of the network here could be a decoder for, or the part of the network that was dealing with French text. So I take the encoding from the English text, give it to the second part of the French network. So let's call the decoder network. So I give the text to the, I give the encoding from the English encoder to the French decoder. What I have got it? I have got a simple translator from English to French. In fact, this was the very first attempt, demonstration of these ideas of transformers. Okay? And now you have seen how transformers have grown. They have become very complicated, and they can do lots and lots of tasks, which is what our generative AI systems are doing nowadays. Okay, and going still further on this generative AI, what we could do, in fact, this is generative AI, right? This is generative AI, because from one input data, we are creating some new data. From this blurred image of a cat, we are creating this sharpened or clean image of a cat. Therefore, we have generated data. So that is generative AI. Okay? So we now build abstractions on this, or wrappers on these generative AIs, which is generally we call agents, okay, to do different types of tasks. Okay, and this is how the entire field has grown. Okay, so I will stop here. Yeah, this is I think this is the last slide. Yeah, so that I was talking about this, right? How we can take one encoder, send it to a different decoder, okay, and then we can have something very different. For example, here is a decoder that was built for face recognition. Okay, and then here is an encoder for audio recognition. So you take the encoder part of the voice encoder, take that as input, and give it to the face decoder. Now what do we have? We have audio that now generates human faces. Okay. Anyway, you have this slide deck shared with you. You could go and look at this particular paper. This, I think, was published in 2016 or 17, around that time. That's when the first version came. It's almost 10 years ago. They have done these kinds of tasks. Okay. So in the very early days itself, you could see a remarkable achievement has been done. This is both fascinating as well as scary. Okay, so you don't need the cameras everywhere. You could, if you could have for surveillance, if you could have just audio recorders, okay, you could record people's voices, and then from that you could probably generate how this person might look like, right? This is like a boon in the hands of surveillance state, right? But anyway, I'll stop here. This is the evolution of the AI, Gen AI in the last few years. I'll stop here. Let's go answer all the questions. Yes, please go ahead. I think, okay.
I'll start. So this is fascinating, but the process from feeding the audio and the face comes out. If I ask a person who's built this, how did this happen? They should be able to explain the technology, or is it the deep neural network kind of thing where they don't know how it happened?
Can you repeat the question? I did not catch your initial part of the statement.
Can you hear me now?
Yes.
Okay. So I'm just combining this slide with what you were saying before about neural networks, that if you ask me this, I don't know. Remember you were saying that what is going on in the hidden layers.
Yes.
So if now taking that point and applying it to this slide, where an audio was used to generate a face. So if I ask the person who built the system or model, can you explain scientifically how did this happen? Should they be able to explain to me, or is it a little bit more complicated than that?
So what they can tell you is, they can tell you how the Lego blocks are built. This is one block for the face network. This is the other Lego block for the audio network. Okay, how these are built. Inside this neural network for the audio, what happens? That they will not be able to explain. Okay, but they can explain how they built this audio part, how they built this image or face recognition part. That they can explain. I used a neural network of 100 layers with a total of 10,765 neurons. I used this kind of activation function. You know, those kind of things they can say. But if you ask you what is happening in the 51st layer, no, I cannot say. Nobody can say that.
Is it a logical explanation? Obviously, there is no magic going on. Hopefully not. But there were so many mathematical equations, so many variables, so many interactions that even though we have fed that computer or fed that model the equations ourselves, but how those equations are working together, we don't know. Is that the right way to characterize it?
That is correct. Your understanding is correct.
Okay, thank you, sir.
Yeah. May I ask what is the significance of encoder decoder in supervised learning? Okay, encoder decoder. Encoding, you know, the word encoding means it's basically a different representation. Okay, we code it, we give it a different code. That's all. Let's think about this image. For example, a simple image, a small image might have I'm giving a very simple example. Okay, an image could have about 3,000 or 4,000 numbers are required to represent a small image which is only about 28 pixels wide and 28 pixels tall. Okay, so that even that might need about 3,000 or 4,000 numbers to represent. Okay, you will see that when we talk about image processing. Yes, speech-to-face.github.io. Thank you, Suvir. Now that is too much, too many numbers. If I can represent the same image using only 32 numbers, that is encoding. Okay, now, okay, I have these 32 numbers. There is no image. I cannot see that as an image. Okay, now I am going to make these 32 numbers, convert them into 3,000 numbers so that I can now reconstruct the image. That is decoder. Okay, how are these put together? Remember, encoder is a part of a neural network. It's a complete part of a neural network. We just take the first part of it. Okay, so that is why during the building of the encoder, supervised learning happens. During the building of the decoder, supervised learning happens. Once these have learned, you just mix and match to do different kinds of tasks that you want. Okay. Okay. Deepak, you had a question.
Hello, sir. This is fascinating content. So if you go back to that slide where you see the input layer, the hidden layer, and the output layer, where you have those neurons working with each other, right? So, I mean,
This one
if
or this one?
yeah, this one, exactly. So if you see like the neurons are feeding into each other, right? Like if even within the input layer, there is processing happening within one neuron feeding into another neuron, and then output of one neuron becomes the input of another neuron. And then there's this hidden layer. I mean, it seems like the function is similar in all the three layers, whether it's the input layer or hidden layer or output layer, in terms of like how the processing is happening. Because initially you give an input, there is some processing happening, there's activation happening, then there's output. How is this different in hidden layer? And like it seems like it's the same in terms of function. It's the same in each of these neurons, right? How do you differentiate like what's happening, what exactly happens within the input layer versus the hidden layer and the output layer?
Okay, the output layer is like a regular neuron. The input layer is just, we call it a layer, but you can think of it as just the plain input. Okay, this will be just x1, this will be just x2, this will be just x3, x4, x5 in this case. Okay, there is no processing happening in the input layer. What we say here is this x1 is fed into every neuron in the first layer.
Okay.
And this connection, we call this a connection, and we call it a synapse. Okay, and what would happen? Usually we would represent this with the weights W1, W2, W3, W4, W5, etc. Okay, so these are just connections, weights of connections would what these lines would denote. And then inside this particular neuron, if you see, it gets one input from x1, one input from oh my god, this is not a fully connected here, this is missing, there should be a line here, one input from x2, one from x3, one from x4, one from x5. So this here is where the processing actually happens. The input layers is where the processing actually happens. Sorry, the hidden layers. The input layer, even though we call it a layer and try to represent like every other neuron, it is basically the variables. That's all it is. On the other hand, the output layer, it is like a regular neuron. It gets inputs from the previous layers, okay, processes them. Now, input 1 multiplied by the weights 1, input 2 multiplied by the weights 2, input 3 multiplied by the weight 3, so on and so forth. So each one of them gets weighted sum and then do some activation and the thresholding and give the output. Okay, that's what happens in the last neuron. So the output layer is where the final decision is made, but it's exactly similar to, or okay, not exactly, it's similar to every neuron in the previous layers, in the hidden layers. Okay, where they can differ is usually the activation functions of the output layer and the activation functions of the hidden layers, they could be different. That's where they differ. Otherwise, they are same. Input layer is just a name, it's just the variables, that's all. Yeah, someone else raised the hand. I did not catch the name. Please go ahead.
I have one, actually, it's not a question, maybe a comment, and just tell me if it's accurate. From input layer to output layer, all that is happening is pattern recognition, but using complex mathematical equation. Is that a fair way to describe it?
Correct.
Okay, thank you.
Correct. It's so complex. It's so nonlinear. It is impossible for I'm going to say use the word impossible for human minds to actually comprehend that. Okay, so that's what you said is correct. Yes. Data loss depends mainly on how the models. Yes, go ahead, please.
So Rajan, until the advent of the Gen AI, right, and the deep neural networks, whatever data was available on the World Wide Web was real data for a good part, right? People shot pictures, posted them. They were real videos. Okay. And now what's happening is that there is a lot of generated content.
Correct.
Okay. And so there is in the generated content, while how much ever an effort is being made to reflect a human mind there through the neural network, there is a distortion of reality.
Correct.
Okay. So whatever outputs that gets generated through this model, how much of it will be factual? Because there is a distortion inbuilt in it.
Okay. I'm not going to answer that question. We are drifting away a lot.
Maybe
from
some other time, Rajan, I can wait.
Definitely. See, you are touching upon a very, very important aspect of generative AI. The data generation is corrupted with lots of things, including the quality of the input data. The data is used. The generated data is in addition to that, these are probabilistic models. Therefore, the output that we get is based upon some kind of probability. No, and so if that is the case, the same input could generate different outputs. Okay, therefore, which one is correct? Generate. I'm not talking about prediction. Generation.
Yeah.
Okay, so generate different outputs. Therefore, which one is correct? We do not know, and this is called drifting. And sometimes, since it's all probability based, these outcomes can be completely unreal, and which is called hallucination. Okay, so we are going into the question that you asked is very, very deep in the Gen AI domain. And what I'm going to do is, please hold your horses for the
Sure.
for 2 courses from now.
Definitely, sir. Thank you very much.
Great. Thank you. We will stop here. We will take a break. There are lots of discussions going on in the chat window. I do not know why this reply is on. Okay, and democratic is getting my call it. Okay. Yeah. So okay. So I'm not going to if I need to answer, if I need to respond to any of the chat windows, chat comments, please let me know. When we come back, let's take a short break. We are at 8:22. Let's say 8:25. 8:35. Let's meet, and we will start on our journey into the alphabets of data science or AI. Okay, so that's what we'll start on when we come back.
How many minutes is that? How many minutes?
So about 12-13 minutes.
Okay.
12 to 13 minutes. We'll take a break for 13 minutes, let's say. Upgrade International has raised the hand. Please go ahead. Oh, no, not that. Atif, do you have a question again?
No, sorry, I forgot to lower my hand.
Okay, that's fine. Okay, we'll take a short break now. We'll be back in 12-13 minutes.
Hi, Doctor Rajan. So I want to ask about when do we have the assignment, the outline of the assignment?
Okay. I have shared the outline of the assignment with the upgrade team. They will release the outline, I think, 2 weeks ahead of the deadline. So your first assignment is usually due after the 8th or 9th session. And the second assignment is due on the last session. I tried to fight with them, but I was given a statement of the sorts like that's the university policy. Therefore, the last assignment will be due on the date of the last session, and the first assignment will be due by on the date of the 8th or the 9th session. And the assignment problem statements will be released 2 or 3 weeks ahead of the deadline. Okay, so that's the standard practice. So you should be hearing this next week or so.
Okay, thank you very much.
Sure. So let me, okay, how could a blur image be sharpened by just traversing the neural functions? Is it similar to lossless function using zip? Well, that's what you're going to learn. Okay, so the trick is that we build a network. Think about this. Okay, that's a supervised learning. So what we take is, we take a clean image, make it blurred or noisy, corrupt it. Okay, some way we corrupt it, send it through the encoder decoder. So what a auto encoder does is, it has to regenerate the original image. Whatever input data is, that's what we need as the output. That's the idea. Now what we would do is, when it gets the output, we are going to say, no, I don't want this, but I want the original image. Okay, we want the original image. That's what we were telling. So it would try to, the auto encoder decoder pair would try to therefore learn, if this is the noisy image, this should be the actual image. No, that's what it will learn. So you will learn all these tricks in the next course, deep learning course. Okay, so please give it a little bit of time. Okay, and somebody, Andy Lee, gives the summary with label standardizing format. Okay, fine. I'm going to stop there. Okay. Yeah. So let me go ahead and start the next session. What happened? Okay. Give me just a minute for me to open the correct file. Okay, I think we are ready for this. Can someone recommend me to some textbooks where I can learn all the concepts with it? John C. Rani, I'm going to suggest not to look for any textbooks.
Okay,
The
sir.
reason is we are going to run. I try to like to keep it a bit slow and manageable, but actually we are running through a lot of different concepts and ideas which might not be available in a single textbook. And when textbooks try to cover all of them, again they might be running through all these different ideas. So there are lots of reference books now which you can read over a period of 1 or 1.5 years time. Now that's the kind of time investment you might need to understand these books, these concepts, if you are going through a textbook route. I would rather suggest that for many ideas that we are going to study here, online reference materials which are there in the handout course plan, they should be sufficient. Or if you're looking for something much more engaging, easily relatable, and in short nuggets, okay, one of my favorite is what is called StatsQuest YouTube channel. Okay, I think that's the name, StatQuest by Josh Starmer. Okay, I have put this in the chat window. Please search for Josh Starmer's YouTube channels. They are very good. Okay, of course, what we used to teach in what is used to be taught in the universities in over a few days of lectures, StatQuest tries to give it to you in about 10-15 minutes time. Therefore, that's also going to be rushed, but at least wonderful animations, beautiful visualizations. So this might be a little bit more interesting. So try that, StatQuest. If you need any specific on any specific topic, so far what we have done is we have just looked at general ideas, and as we move on and on, these ideas will actually solidify. You don't have to worry about that. But when we talk about a very specific topic, let's say we are talking about decision trees, let us say, okay, and if you want reference material for them, you can ask them for decision trees alone, what could be the reference material. I would try to find out and tell you, for example. Okay, so that would be my suggestion. Don't go in search for a textbook for the overall course. That will usually not work, because the field itself is very new, and it's growing at an enormous pace. We all know that, changing at an enormous pace. And in addition to that, the textbooks usually focus on the theoretical foundations. Okay, and for example, when I was a grad student, I think I mentioned in the last session, when I was a grad student, when I used to spend many hours in the library, university library, I had seen, read quite a few books on neural networks, books, 300, 400 page books on neural networks, on one topic in neural network called backpropagation, all these things. But what happens? We are going to study that in half a session. We are going to learn that in half a session. So the disconnect might be huge when you go to the textbooks. So I would say, treat textbooks if you're ready to dive very deep in to these ideas, go for textbooks. Otherwise, online reference materials are sufficient for the purposes of this course. Okay, that would be my suggestion. Okay, now let's start the next topic. What we are going to do is we are going to look at statistics. Okay, statistics is one of the foundations of modern data science. So we are going to look at statistics and probability. Okay. I usually like to start this section with this particular question. What is statistics? Okay, let's have a quick 5 minutes discussion on this. What is statistics?
Characterization of non-deterministic outcomes.
Characterization of, oh my God, this is so ugly. Let me change this to liberation. So if I like Laura, let's get to 18 points. Okay, characterization of non-deterministic outcomes. Can you say what is? Who said that? I didn't.
Nias.
Nias, I think you should let others. Okay, I shouldn't say that. Even that is considered uncouth nowadays. But anyway, let's wait for others' opinions.
Using data on tools for us to make outcome, but to make decisions.
Data to
using tools on data to make decisions.
On data to make decisions. Okay. Anything else? I would like to say
using quantitative methods to make sense of the world.
This is like how a European philosopher would state the statement. Well, anyway, so sorry if I
is the science of learning patterns. The science of learning patterns and then making decisions from data.
Okay. That's I heard someone else also say something.
It's the same, maybe like Sam saying. It's like something like collecting data just to get some patterns or to understand patterns to make decisions.
Okay. Collect data to make some decisions. Okay. Okay, I'm going to stop here. Usually I spend about 15 minutes to see a variety of responses. What I've heard in previous sessions, previous cohorts, somebody would say creating visualizations, Somebody would say doing analysis. Somebody would say, building models, a variety of things. And for each one of them, I have a counter. Let's say using tools on data to make decisions. Okay. Can we use tools to make decisions regarding galactic bodies, intergalactic bodies? Okay. Then why do we call it astronomy or astrophysics rather than statistics? Quantitative methods to research the world. Okay. Let's say I want to understand how much first impressions are important in hiring. Okay. So I interview or I send out a questionnaire to quite a few HR and quite a few new job applicants and collate the data, do something. Okay. Why is it called a survey, not statistics? Learning patterns and making decisions from data. Okay. People study how the coastal lines are. Okay. How do the coastal lines emerge? How do they generate? What is the genesis? Okay. How do different terrains get formed? That's pattern. Why is it called geology and not statistics? Okay. Collect data to make decisions, generalized. Okay. So now when I ask questions like that, then some uniformity, some commonality emerges. And what is the commonality that emerges? That's what Niaz said in the very first opening statement. Characterization of non-deterministic outcomes. I don't want to even say non-outcomes. Okay. Let it be there, but I'm going to say it a slightly different manner. Okay. So I usually give 2 questions to people and ask them to answer these 2 questions. Okay. You don't have to answer. Okay. You don't have to answer this, but you can see the difference in the quality of the question. Okay. Okay. Let us say you are living in the city of Mumbai, and let us say you are a senior vice president of a company. Okay. So you are a senior vice president of a finance company, let's say. Okay. So now I ask 2 questions. Okay. What was your take home salary last month? You don't have to give me the answer, obviously, right? What was your take home salary last month? That's one question. Okay. The second question is, what was the take home salary for a senior VP in a fintech in Mumbai last month? Okay. Which question is easy to answer? Question number 1 is, what was your take home salary last month? That's question number 1. Question number 2 is, what was the take home salary last month of a senior vice president in a fintech in Mumbai?
Question number 1.
The first one is easy. Why?
Because where our data is very less and data points are very less, so making a decision very easy.
When you say very less, what is it?
Data.
How many?
Only 1.
1. That's 1.
Yes.
There is no doubt in that value. Correct? I took home 250,000 rupees last month. Okay. So 2.5 lakhs last month I took home. Last month I took home 75,000 rupees. That was my take home salary. Okay. Fixed number. Very clear. There is no doubt. But if you, on the other hand, the second question, we have no single answer. Why? Because there are so many fintech companies in Mumbai. and there might be more than one senior VP in a company. And unless we list out the take-home salary of all these people, we don't have an answer. Okay, we don't have a single answer. The absence of the single answer arises not because, okay, the absence of the single answer, that is called non-deterministic. That's what he said. Deterministic, single, very clear. There is no doubt. Okay, but on the other hand, the second question, you cannot give a single answer because the numbers are varied. The numbers are varied. So you cannot give a single answer. So statistics is a study of uncertainty. What do I do? What did I do here? Uncertainty. Okay. So when we do not know, align objects centered, make it centered. Okay. When we do not know for certainty what the answer is, then whatever answer we should give, how do we know that? That is when we use statistics. Okay. Usually, the uncertainty arises because no single answer exists. Okay, a range of values exist, but not a single answer. Then let us think about this. Okay, let us say there are only about 45 senior vice presidents in Mumbai, in fintechs. I'm just saying some random numbers. Okay, some 45 senior VPs in Mumbai in fintech. I have done some Herculean task or Bhagirath Prayatna, and what I have done is I have got these 45 numbers and I give it to you. I list out all the 45 numbers. How much sense can you make out of those numbers? It's the second question. The human cognitive ability, it's uniform. There are outliers who might remember all these 45 numbers on a single view, but normal human beings, they cannot make sense of these numbers. That's the 45 numbers. But let's think about a different situation where we are going to look at all sales representatives, medical sales representatives in Mumbai. What was the take-home salaries? That runs into thousands, if that's into hundreds, if not thousands. Okay, so now the only correct answer could be listing out all the numbers. Listing out all the numbers. But that's ridiculous because we cannot comprehend that. Therefore, what should we do? We should give few numbers. We should give few answers. Okay, the salary could be, something like the take-home salary for a senior VP in fintech in Mumbai could be 175,000 rupees per month. You have a comma there. The way you speak itself tells you that there's a comma. Why? Because that's just some number, which might be true or not true. But then you can go ahead and say, with the lowest being about 75,000 and the highest being about something like 750,000. Okay? Something like that. So now what you have done? You have answered this question. You have answered this question and you have implied that there is uncertainty. How did you imply that? By giving more than one number. Okay, and these numbers, except for the minimum, the lowest value and the highest value, the sum number you said, could be, you said the take-home salary could be 175,000. How do you get that? Why do you say 175,000? I ask you. Then you say, give me the answer. That's a representative number. No, it's not real Nobody actually makes 175,000, but it's a ballpark. That's a representative number. That's what we say. What do you mean by representative numbers? In statistics, we have very specific names. These are the other names. In statistics, we have very specific terminology for these representatives. The representatives are called central tendencies. Okay, central tendencies. We all know this. We have studied these quantities from our 10th standard. Okay, so mean, median, mode. Okay, we can give the representative numbers. So when I say 175,000, then maybe I meant the mean. It's also called the average. Or maybe I meant the median. Okay, usually not the mode in this situation. Should I say mean, or should I give them, for such questions like this, should I answer with the mean, or should I answer with the median or the mode? When do I use mean, median, or mode? That's a question then we'll have to ask. I also gave you this thing about, with the lowest value being 75,000 and the highest value being 750,000. So I have given the range. That's called measure of dispersion. The values are dispersed over this range. Okay, so measures of dispersion, there are multiple measures of dispersion. So what should we do when we talk about uncertainty? Because a single number is not a good answer, because single answer does not exist, then we have to give the central tendency and also a measure of dispersion. Both of these have to be given so that we get an answer. And these two, only these two, if you understand these two, that's it. That's all statistics is all about. Central tendencies, measures of dispersion. Okay, central tendencies, measures of dispersion. Why do we do this? Because we are uncertain. Why are we uncertain? Because a single answer doesn't exist. Multiple answer exists. Why multiple answer exists? Because that's the nature of the question. That could be one thing. It could be due to another thing. Namely, let's ask the question that what is your height? Okay, let me ask you a simple question. What is your height? You might come and say, okay, I am 173 centimeters tall. Okay, I am 5 feet 8 inches tall. Okay, but then I ask the question, are you really 173 centimeters tall? I ask you that question. So I make 10 measurements. Every time I make a measurement, I get a slightly different number. Sometimes I get 173.2. Other time I get 169.7. That's one thing. I make a measurement, I get 173 centimeters. Somebody else, okay, Niaz makes a measurement, he gets 174 centimeters. I saw another name. Sam measures, he gets 169. So there could be differences in the measurements due to various reasons. Let's not worry about why. The same. Your height is one fixed number. Your height is one fixed number. You cannot be, varying your height every second. Right? You have a fixed height at any given small window of time. Even within that window of time, when I make measurements, things could change because each one measures slightly differently. We get different numbers. That's another question of uncertainty. So uncertainty could arise because of two issues. The answer itself is uncertain. The second thing is uncertainty could arise because of measurements. Whatever be the reason, if there is uncertainty, then we have to resort to the tools of statistics, namely central tendency. Let me make it bold. Central tendency and measures of dispersion. Okay, so we'll discuss all these things, central tendencies and measures of dispersion, in the next few minutes. Yeah, we have some time. Okay, On the other hand, we call it, many people say it is the other side of the coin, and that's a very interesting pun, because whenever we learn probability, we always start with the toss of a coin as an example. Okay, one side of the coin is statistics. It talks about what has happened in an uncertain situation. Probability, we usually talk about what could happen in uncertain situations. Okay, so these are the two sides of the coin. The twin sibling of statistics is probability. Okay, so what is probability? There are multiple definitions, but you all have an intuitive idea of what is probability. Okay, and we will learn about all these different ideas. We are getting close to the end of the session. We have about 7 minutes. Let's see how much we can move forward. Okay. And this is a very fascinating subject. Okay, I hope I help you fall in love with this subject once again in this course. Okay, and finally, this is again what should be stats. Let me make statistics probability. Even though statistics and probability are considered as two sides of the same coin, sometimes we combine them together. Okay, because let's think about this. Okay, I ask you a question. What is the salary of a sales representative, medical representative in Mumbai? Medical sales representative in Mumbai. Okay, there are like 3,000 medical sales representatives in Mumbai, but of course you cannot go get all their data, so you get a sample. Okay, you get a sample. You talk to 30 or 40 sales representatives and convince them to reveal their secrets, and they tell you their monthly salary or annual salary, CTC, no, whatever. Okay, now what you do? You have a number. You have some sample. Okay, you have some sample. So the sample has some range of numbers. So from that range of numbers, you can get one representative value. Okay, and what you are interested in is, you are not interested in just the sample of 30 people, but you are interested in the entire 3,000 representatives, right? Sales representative, all the 3,000 sales representatives in Mumbai. That's what you are interested in. The sample says the mean salary is 85,000 rupees per annum, sorry, per month, let us say. 85,000 rupees per month. Now, you are not interested in that. You are interested in Mumbai, the entire Mumbai. Can you just say that the average salary of sales representatives, medical sales representatives in Mumbai is 85,000 rupees per month? You cannot say that. That is true for the sample, but not for the entire group. The entire group is called the population. Now what you want to do is, okay, I have the sample. Now I'm going to hypothesize. I'm going to hypothesize that the average salary of medical sales representatives in Mumbai is 65,000 rupees per month. Okay, that's what you are going to hypothesize. Okay, well and good. 65,000, 85,000, 95,000. No, you say tomato, I say tomato. Let's call the whole thing off. No, you cannot call the whole thing off. Now you have to go check whether your hypothesis is valid or not. Because why do you hypothesize? You hypothesize because you want to take some action based upon the hypothesis. Okay, so the government is thinking that these people are always on the road, therefore there's a lot of stress on their physique. Chances of their road accidents is higher than the average population. Therefore, we should insist that the companies should increase their medical premium. right? Something. I'm just thinking about something. So you want to make some decision based upon this hypothesis you are making. So you want to now go and validate whether your hypothesis is valid or not. You want to test whether your hypothesis is valid or not. And that is where you use the statistics, because you have the data from the sample, and use probability. You use the probability. What do you say? What is the probability that my hypothesis is valid given this data? Okay, you calculate the probability. If the probability is high, then you say, okay, I'm going to work with this hypothesis. If the probability is low, what is high, what is low? Again, you have to come up with a threshold, a boundary between low and high. Okay, and if it's low, reject the hypothesis, start with a new hypothesis. Okay, so that's where this is the overall idea of hypothesis testing, right? So you bring in statistics, which is what you measured on the sample, use that to make a hypothesis statement about the population, the entire group, and now calculate whether you have enough support in terms of the probability of your hypothesis being valid given this data. Okay, that's what we do when we do something called hypothesis testing and confidence interval. All these things forms the foundation of the entire data science edifice we build. Okay, therefore, we are going to spend decent amount of time understanding these things. Okay, let me make it bold. In this, when they don't look neat. Okay, what is statistics? I'm going to, sorry, I'll share my collection of responses from previous cohorts as well. Okay, so what is statistics? Control B. And let me go and change it to different color. Okay. Yeah. So I think we are at the correct time. It's 9:15 on my watch here. That means we are at the 2 hours 45 minutes boundary for this class. I think we are at the right time to call the day of today. You have a lab session tomorrow. Okay, the lab session, you will learn a lot of things. I think you are going to learn about these ideas, central tendency, variance, and a few other things, dispersion, central tendencies, and how to use Power BI. If my memory is correct, that's what you are going to do. Or the lab faculty might start directly with Azure, MS Azure. I do not know how this is going to be, but that's an introductory, hands-on things for you in this statistics course. So tomorrow you might get to talk about all these things that I am supposed to cover in this lecture, but unfortunately, since we have been talking and talking and talking, so we are running a little bit late, but you will learn all these things. Next week, when we come back, anyway, we will discuss all these things and get a deeper understanding. I will share this PowerPoint slides, this slide deck with you. Obviously, I will convert it to PDF and share this with you. You can go ahead and go through it and use it tomorrow and come prepare the next session. Okay, so I'll stop here. If there are any questions, any discussion points, let's continue. Otherwise, you all have a great weekend ahead.
Rajan, quick question for those who've already attended the lab session yesterday. We're still continuing with the pre-scheduled class for tomorrow, same time, right?
Yes, the same time. The lab will be at the same time, 6:30 p.m. India time.
No, I meant for the lab session happened yesterday already. The first session already happened yesterday, and they're doing three slots.
What happened yesterday?
They did the introduction to Microsoft Azure.
Okay.
That already happened yesterday, happening tomorrow morning again and tomorrow evening again. Sorry, I'm talking in IST hours again. So
Correct.
for those who attended yesterday, tomorrow morning and tomorrow evening is a repeat of the session that already happened yesterday. So for those who attended yesterday, are we logging into session 3 for our
Yes. So see,
yeah.
session 3 is different from that. That is an add-on training. That's not part of this course.
No, I'm talking about the
Tomorrow's session
foundation
at 6
Yeah.
p.m. India time is part of this course. The MS Azure session you had is an add-on session. It is not part of any course.
Got it. So we're logging into the pre-scheduled session of this course, which is Foundations of ML and AI tomorrow at the same time.
Yes, correct.
Got it. Thank you very much.
Yeah. John Sirani and then Mohammed Niaz.
Yeah, thank you, sir. Actually, you gave this presentation. Thanks a lot. You can upload this presentation. Is there any other timing you go through this presentation, or we have to learn by ourselves those? Because you said due to the timing, you cannot able to go through this sessions. Is it the last slide deck? So is
You
there any
mean
other
to-
time? The statistics and pro.
Yes, you
Yeah,
mean to say, let me say, I'm not able to cover this. Let me share my screen once again. So do you mean to say these slides I'm
Yes,
not able
these
to go
slides.
through?
Yes, sir. Yes,
We
yes.
will go through them next week. The next session,
Okay.
tomorrow, it's going to be lab session.
Okay.
Okay. The next Saturday, 1
Okay,
week
sir.
from today, is my
Okay.
session.
Okay.
We will go through this.
Wonderful. Thank
We'll
you.
go through.
Thanks.
I'm not going to skip this. We will go through this. I'm
Wonderful.
just
Thank you.
saying, I will share this anyway with you today, right away. You
Okay,
can go through
okay.
it beforehand. That's all.
That would be very kind. Then I can at least do some homework to better understand. Yeah. Thank you.
Sorry if I didn't make it clear. Sorry. Okay, we will go through the entire thing. Don't worry about it.
Super.
Mohammed
Thank
Niaz?
Yes, Rajan. One question with respect to the intermediate layer functionality of the dense neural network. Like when I was experimenting some code, there I have seen, for example, in the CNN, there is a layer mapping functionality which gives the intermediate layer what kind of a transformation it does and so on. For example, like it detects the edges and higher level aggregation of edges and so on. So that way, we it was given in the perspective of how to arrive at the optimal number of layers. So in that sense, we have a crude view of what functionality those intermediate layers adopt, right, Doctor?
Okay, so CNN is very special in that sense because we design the neurons such that they extract these what we call features. They are designed that way. Therefore, CNN has some amount of explainability.
Okay.
But
okay.
deep neural networks do not. Okay, deep neural network in general do not, but CNNs do have because they are designed to have this kind of property. This comes from trying to mimic exactly the human visual system. Okay, that's where this comes from. So in that sense, CNN has a little bit explainability, but other deep learning networks, they do not have.
Got it. And another thing is, I had this question, but then it got answered when you were discussing. The deep neural network cannot be used for unsupervised learning. Is that a correct understanding?
Yes.
Because why I am coming there is the weights need the error value. Only then it can get it. And okay. And another thing, if we are looking at the back propagation, the back propagation basically propagates the error and it tries to arrive at the intermediate layer's error value, right?
Correct.
So that way it brings a determinism to the intermediate layer's expected output, right? So that brings, at the time of back propagation, the intermediate layer, what it does is known to the back propagation algorithm. Is it correct?
Yes, in the sense that what a particular neuron's bias or its weight in relation to its connection with another neuron, that is known. Okay, during the back propagation aspect. But then, what does it actually represent in terms of what it has done to the input? That is not explainable. Say, for example, in a simple linear regression model, I should not say simple linear regression, in a linear regression model, you could say that after some, in certain situations, that variable 1 is more important than variable 2 because variable 1's coefficient is much larger than variable 2. This is only in certain situations. Okay? So variable 1 drives our model. So that's important variable that we can say. But however, in neural networks, we might not be able to say that because what the neurons do in between, that information is lost because of the humongous amount of non-linearity that goes in there.
And one more question, Rajan.
Let me give a disclaimer, folks. This is way beyond what Niaz is discussing. Is way beyond the scope of this particular course. So if you want to just leave, please go ahead. I would usually say let's discuss it in the next course, but I'm kind of interested in the way he's asking the questions, so I'm staying back and answering. I enjoy these discussions. If others have questions that are direct to what we have discussed in the last 2 sessions, please go ahead and ask them. Otherwise, you are free to leave. We will see you next week. Okay. With that disclaimer, Niaz, please go ahead.
Sure. And the neural networks, they require the normalization of the input for its optimal performance. Now,
yes.
Whereas the normal, regression network, they are a bit resilient to that.
Correct.
Now, so that means that I can use a neural network model only when I know the min-max or the characteristics of the signal. Otherwise, I am bound to use the tree-based or the classical machine learning methods.
You could do that, but whenever you can do the min-max normalization, okay, you could always do that. This ability to not do, or the inability to do min-max, is applicable only when the input variable is categorical. Okay, if it's a continuous variable, you can always do a min-max normalization. Okay? But once you have passed through one neuron, the output of a neuron is always a continuous number. It's an activation function. It's a continuous number. So the outputs of the neurons, before they go to the next layer, they can always be normalized. And that's what they do in the normalization process.
Sure. Thanks, Rajan.
Sure.
Thank you.
Okay, great. Thank you all for your patience, and it's session 3 GU slot 2 foundation. Yes, that is one. Okay, it is there. So I'll see you next week. If my time allows, my family allows, I will join in surreptitiously tomorrow to see what happens in the lab. Otherwise, I will see you next week.
Rajan, tomorrow evening there is a session, right? And
correct. That's a lab session. Yes. My understanding is tomorrow's lab session will be an introduction to statistics probability using simple, ideas in Power BI.
Oh, that will be taken by Dr. Saroja.
Correct. Dr. Saroja Nagarajan. Yes.
Sure. Thanks, Professor. Thank you.
Great. Thank you. Thank you all. Take care. Bye-bye.